Somebody saying something, but I cannot hear it. It's breaking. Breadth of the web. Okay. $250. Grades are M20 and okay, so finally I have been able to find out what are all the details given. Okay, so what we want to do is we want to find what is the moment of resistance of this particular section. Okay, of the ultimate moment of resistance. This is what we want to find. Okay, so as before, now first we'll start with assuming that it's going to be under reinforced and being within the rectangle. The flange being more than the location of the neutral axis. Okay, such that we can assume it to be a rectangle. So that's the assumption that you will start with. But before you started with it, we have to find out what is the effective width of the flange. So again, if you go back to that class which is told, okay, the class number 23.1.2 for finding the effective width of the flange. So this is for full isolated. These are for T beams which are not isolated. Okay, this formula is for beams which are not isolated. The same class, if you go to part number 2 of the same class, you will have one more. This will be class 23.1.2A is this one. Class 23.1.2B is for isolated flange sections. Okay, so there you will have a different formula. You can just open the code book, you will find it. And that code book says that for finding this kind of a sections, the effective flange width is given by L0 divided by L0 by the actual B which is given. Where is B given? Here it's given. Okay, L0 by B plus 4 plus width of the web. L0 is 6 meters. The actual breadth of the isolated T beam is 1000 mm. DW is 250 mm. So get me what is the actual effective width of the flange. Okay, so basically the T section is like this. D, oh my god, DF I have not mentioned, have I? Okay, where is DF? Mm-hmm.
850 mm. Sir.
How much?
850 mm.
Yeah, that will be 850 mm. So just a minute, I haven't given you DF. I'm searching for what is DF. Well, what DF is given to us, I'm searching for that. I should have checked this before I sat for the class, but anyway. I suppose it will be 100 mm. I think it is should be 100. Yeah, 100 mm. I've written it in such a way that even I am not able to find it. Okay, so the actual one which is given to us is 1000. Okay, this is another 600. So if I have my reinforcement here, then this is 520. This is 100. This is 250. Okay, so these are the things that have been given to us. So this is found, as somebody told me, it will come as 850 mm. Okay, so this is the first thing that you had to find. Next thing, let us just calculate. Just calculate this total area of steel. Let's keep it with this. How much is AST? Six numbers of 28 diameter parts. How much do you get?
So 3694.
3694.
94.
Okay. Maybe, I don't know. So maybe 3694. So this has also been found. So first thing that we're going to see is what is our XU max, and so our XU max equals something times D. Here, however, it's a mild steel. It's not even HY steel. This is mild steel. So does anyone by chance know what will be the number if it is Fe250? How much is it for Fe415 and Fe500?
0.48D for Fe415.
Okay, 0.48, and for the other one, it is how much?
0.46.
0.46. So for Fe415 it is 0.48. For Fe500 it is 0.46. So Fe250 is even lower grade steel than Fe415. So will that constant point something, will it be more than 0.48 or will it be less than 0.46? So we know that Fe415 is 0.48. For Fe500 it is 0.46. So for Fe250, so Fe250 will it, so will you have a higher value or will you have a lower value for Fe250?
So it will be higher value, sir. Approximately 0.52.
0.5 how much?
0.52.
0.52. Actually, it is, you're close. It's actually 0.53. Okay. So 0.53 times D is if you have this kind of a steel. So 0.53 times 520. How much is the limiting depth of neutral axis? How much is the limiting depth of neutral axis?
275.6.
275.6 or 276? Let's keep it as 276 mm. Okay. So we have found this. Now with this we'll start our usual procedure. Let us assume first that the neutral axis lies entirely within DF. I should not say neutral axis. Okay, lies within the depth of the flange. This word entirely doesn't make any sense. Okay. So basically what I mean is, the first, of course, I'm assuming that this is my thing. Then I'm having my slightly redraw this. And I'm assuming a case where it's like this, and my neutral axis is actually here. Okay, where this is DF, and only this much is XU. Meaning that only this much of my beam is going to be effective, as told before, and therefore I can assume that it is going to be like that means it is like a rectangular beam, and we can find out what is actual XU. Okay, where actual XU will be given by, if it's a rectangular beam, what's the formula for XU? What by what?
0.87 FY AST by 0.6 FCK B.
FCK, what should you put for B here?
DF, sir.
DF or this one?
Whichever is less, we have to take.
Yeah, having the effective one which you have found, you will take that. So this is BF. Here will be using BFE. Okay. So anyway, 0.87 is known. FY is 250. Be careful, don't put 500 or 415. AST you found 3694. FCK 20. Level 350. How much are you getting for?
So 131.28.
131.2 mm. And as you see now, this is actually greater than DF, and therefore this assumption is not right. Okay. So we move ahead and go to assumption number 2. Okay. Where just like the previous problem, we this time assume that our flange lies in the, now I'll say flange lies entirely in rectangle of stress block. Okay, so means this is my, every time I'm just drawing my flange differently so that I'm able to accommodate the assumption which I mean. Okay, so this lies entirely within the rectangle. Okay, meaning that so this part is a rectangle. Neutral axis is here. So only from here the parabola starts. So it's this flange is entirely within the rectangle. This is XU. This is DF. Okay. So if this is the case, we know that if this is the case, that means my XU is greater than 7/3 of DF, or this value equals, I think it will be same 233 or something. Okay. Okay, this is what it would mean if that is the case, and it would also mean that YF, which we will require in the formula, will be equal to DF, which is 100 mm. Okay, so now using this we can do the same formula and find out the compression force and in the web and in the flange. So CUF, which means the compression force in the flange, will be 0.36 FCK B. I will leave it at B. You have to tell me what B it is. Okay, into XU, and CUW equals, it will be, it will not be 0.36, it will be some other number. Okay, and there will be B something here times YF. Okay, now question is, what B is this? Is this BF or BW, or is it entirely B? What should be the subscript here? Sorry, I used the wrong. What B is this?
0.446.
You're telling for this one. .446. What is the subscript of B in this one? BW or BF? What will come here? E what? Somebody's mic is that problem with me, I don't know.
VW, sir.
Yeah. Krishna, yeah, Krishna Yadav. Now it's fine. Okay, let's not waste too much time. So it will be BW, and here you will have what we have here. So this is the component force for CUW. Sorry. Small thing. So this is CUW, and CUF will be the component force in this part. So what will it be here in this bracket? What width do you multiply it by?
B minus BW.
BF minus BW.
BF minus BW. Yeah. BF minus BW. So yes. Now just like yesterday, I would ask you to retain these two things in terms of XU so that we can use it in our next part also. So you get me this in terms of something XU.
Sir, FCK.
FCK? FCK. Thank you. So XCK 20, BW is 250, XU is XU we're going to find, but not find, we're going to keep it as XU 20. This will be 600. BF minus BW will be 850 minus 600, and still retain it as YF. Yeah, so how much is CUW in terms of XU? How much is CUF in terms of YF? See, we'll be doing only one problem today, so the sooner you answer me and the sooner you finish it, you get free time. At least for the sake of that, just for the sake of that, at least give me some quick answers.
1900 XU.
1900,
800, sir.
1800, okay.
352 by F.
5352.
5352.
52.
Yes, sir.
Okay, so this is general equation for getting CUW and CUF, and you can also find out the tension force. We already know the area of steel, so you can find out tension force, which is 0.87 Fy AST. Okay, so how much is the tension force? This you don't need to keep it in terms of AST or Fy, you give me the actual number itself. So basically what you're finding is, we are finding so there's a CUF part, there's a CUW part, and this is T. Okay. This lever arm is given by Y. So you'll get the lever arm for this.
803 kilonewton, sir.
0.4 kilonewton.
Point
803.4 kilonewton.
803.4. Okay, so let me keep it as 8. This much newtons.
Yes, sir.
Yes, sir.
Fine. Now for this particular case, for the case where when XU equals 233 and YF equals 100, C which is equal to CUW plus CUF equals how much? Just multiply this by 233, multiply this by 100 and add it. Sorry, I mean, what am I saying? See, we are finding XU, we are not keeping it at 233. Our target is to find XU in fact. Okay, so you'll get something times XU plus some number given by this. Okay, how much is that? Okay, because we are making the assumption that XU is greater than 7 by 3 DF. We are not saying that it is exactly at DF. Sorry, 7 by 3 DF. In design, we can kind of take that approach and say if XU is at exactly 7 by 3 DF, are we getting the moment that we want? So in design, you can do that. Here, the steel is also already given to you. So you cannot simply say that neutral axis is at some location. You have to actually locate the neutral axis. Okay. What I have mentioned here is this 7 by 3 DF is 233 mm and XU should be greater than that. Okay, XU might be greater than 233 mm and we are checking for that. Okay, so in design problem you will say that let XU be at 7 by 3 DF itself and you will check whether you get the moment which is required and you do all the other things which you did in yesterday's class. But in an analysis, you actually have to locate exactly where the neutral axis is for the given reinforcement of steel and for the given dimensions. Okay, so you'll be retaining XU and you'll be finding it. YF, when you have such a case, YF is always equal to DF, so you're just substituting that. So CUW plus CUF. So you'll have something XU plus some number. So what is this? So it will be 1800 XU only because XU you are finding. How about this other number? 5352 times 100, how much?
535200.
00. Okay. So what you now say is for equilibrium, C equals T, meaning that this tension force which you got 8.3400 equals 1800 XU minus 535 200. Okay, and from this you can see what is XU and you can check whether this assumption was right. Okay, how much do you get XU? Okay.
149.
149. Okay, anybody else gets 149? Just take it. 149.
149.
It's a 149.
149. Okay. Now let's compare our assumption with what we got.
So actually shouldn't be like 1800 XU plus 5353210.
Plus, sorry, okay. Sorry, okay. Plus, it should be plus. Anyway, now you got XU is 149. How does it compare with the assumption that you took? Is the assumption right what we took over here? Is it satisfying this? Whatever we found? Is it satisfying it or not?
No, sir.
No, we assume that it should be greater than 7 by 3 DF, greater than 233. We got one, but for that assumption, when we actually find the neutral axis, we are getting only 149, which is actually less than 7 by 3 DF, and which means this assumption is also not right. Okay, so therefore you can conclude. Therefore, the flange. I'll put it therefore the flange lies partly in parabola of the stress block, meaning that our thing over here actually it's not like this. This assumption is not right, and rather we have something like our stress block is a bit different, and the actual case is such that there may be something like this. Okay, partly in the parabola. This is where the parabola starts. And neutral axis also it will be somewhere else. It will not be this below. Neutral axis will be a little bit above then. Okay, so this is XU and this is DF. So now we have this issue and we have to now use the bigger formula which we had. Okay, so therefore in this case my YF is given as 0.15 XU plus 0.65 DF are again 0.15 XU plus 0.65 times 100 is 65. Okay, so you will have to use this and you will have to actually find out what you get. Only thing what will happen is here now CUW which you had, that is no problem. CUW will still be 1800 XU. But only problem is now CUF is also not a constant. Okay, it will not be just simply 5352 times 100. It will be in fact something else. So it will be 0.446 into okay, why am I doing this? 5352 times 5352 times YF is 0.15 XU plus 65. Can you just expand this and tell me how much do you get? 5352 times 0.15 XU plus 5352 times 60. Expanding this, what is the expansion that you get for this? What XU plus what? Yes, we are nearing the end. It's a
So 802.8.
802.8 or about 803 XU.
Plus
Okay,
347,880.
347. Okay, others also just check whether you get this 803 XU plus 347,880. Okay, so the rest of the problem is same. Nothing much to do further except we going to again apply equilibrium. So CUW plus CUF. So which will be nothing but 1800 XU plus 803 XU plus 347,880. So again something XU plus 347,880. So what is 1800 plus? Just add these two, you get about 2603, I suppose. 26. It should be 2603 XU. Okay. This should be equal to, for C equals T, this should be equal to 803 400. Meaning XU is, what do you get for XU? How much is the neutral axis location?
75.
75.
25.
Just 75.
175.
175, sir.
75. Okay. Okay. Now. So this was our condition. So the one which we obtained, does it actually fit into this XU which we have found? Is it fitting or not fitting? If it doesn't fit, then we are gone. We are run out of options. If it doesn't fit, does it fit or not?
Fitting, sir.
It's fitting, no? Yeah. So this is within the range. It's more than 100. It's less than 233. So therefore, this actually fits. And this is the actual case which is present for this number of steel bars for these dimensions of a T section. So with this, you'll have to find again. You'll have to evaluate YF. 0.15 times 175 plus 65. So how much is this? How much is YF?
91.25.
91.25.
Let me keep it as 91 mm. That's it. So we just have to find the moment of resistance now. So it is given by the formula of the moment due to the web part, which is 0.36. Okay, write both of them just for your understanding. BW XU times D minus 0.416 XU plus 0.446 FCK BF minus BW to YF into the lever arm, which is nothing but D minus YF by 2. Of course, many of these things we have already found. We have already found that this whole part is nothing but 1800 XU into D minus 0.416 XU. And this part we found it is nothing but another 8.3 XU. What was it? It was 5352 YF. Okay. 5352 YF into D minus YF by 2. Everything here is known to us. Okay. This 1800, I hope you remember, it's nothing but CUW value. This is nothing but CUF expression. So this we have found. This is 175. This is 520. XU is again 175. YF we found 91, 520, and of course this will be 91 by 2. Okay. So you can give me what moment you get. How much is the ultimate moment of resistance? Hello? Am I connected or have I lost connection?
So you are
Because temporarily my connection just went and returned. That's why I asked. Anyway, moment of resistance.
2.5 kilonewton meter, sir.
Okay, all this also check whether you get 372.5 kilonewton meter. Okay, it's the right answer. So anyway, so that's it. The problem is over. So anyway, two problems we done in plan sections. So because we did two problems, I think now you will be a little bit more familiar with these three steps. Okay. So depending on what type of a beam that you get, if you're lucky, you may be able to stop with this step itself. If you do it once and you find out it's working. If you're slightly less lucky, you will be able to stop with this step, and if you are extremely unlucky, you will have to do this whole steps. Okay, depending on what problem is given to you. So anyway, whatever is there, I think now you'll be a little bit familiar with what all this means and why we use these three steps and check each of them. Okay, so the problem is over. I'll unshare the screen. If you want to ask something, you can ask, or I can close the class.
Sir, a problem in doubly reinforced LSM design, sir.
Okay.
We didn't get the correct conclusion, sir.
Which one? Which problem?
M25 FE500.
Okay, let me just check. Done last week.
Yes, sir.
Which one? This one or previous one? Which one?
Yeah, this one, sir.
This one. Okay. Which part of it?
The final conclusion, PC is less than PC limit we got, sir.
Oh, you got like up here. PC in okay. PC you got less than PC limiter. PC.
Yes, sir.
Point. This is PC limit. Okay. We are getting both 0.8 or something lesser than 0.8 you're getting here.
PC limit is 0.955 we are getting, sir.
Oh, PC limit is coming 0.955, actual one.
Yes, sir.
Hey, no, see, I have told here, no. So I told you I made a correction, right, for FSC.
Yes, sir. After correction only, sir.
So here after making this is 412.
Yes, sir.
Oh, you are getting 0.95.
PC limit is 0.95.
After making the correction itself. Yeah. I didn't know that 1.68 minus 0.94 into 0.87 into 500 divided by 412 minus 447 into 20. No, I get 0.8 if I make that 412. Just put 412 there and see. I think you'll get 0.8. I'm getting 0.8 only. Just check it once, boy. Just substitute 412.
PC limit is 0.8, right, sir?
PC limit?
PT limit is 0.8, no.
PT limit. You're telling T limit or C limit? Oh, this PT limit. Where is PT? PT limit. I don't think it did change. If 500 PT limit will be around 1 point. Point something or other. PT limit. I would have checked somewhere. 0.94. See, we used 25 and 500 here only here. It's correct only. 0.94 PT limit is correct.
Okay, sir.
PT limit here. And if you look at PT limit calculation, I had not made the mistake of putting this as 415. We had used 500 as should have been used. and we got 0.94. The mistake which was made was in calculating in this part where instead of looking at the FE 500 table, I had looked at the FE 415 table and I put this value of FSC. Okay, so that's why that mistake was made, and then I corrected it, seeing that the actual steel is FE 500, not FE 415. Then I changed this. Then from that I got PC limit as this, and in that calculation PT limit which we use over here 0.94, that was found correctly only. I had used 500 only over here. It's correct only. Okay. Can you do a problem? You'll be familiar. Whenever a mistake happens in a problem, it will tend to confuse.
Sir, I have a doubt.
Yeah.
Sir, like for the effective span, like should we take the minimum of the center to center distance or the clear span plus the effective depth?
Whichever is lower.
Sir, but then in these questions, like we took like 7.05, but then the center to center design.
It was lower. Oh, okay, fine. Yeah, you should have taken. Okay, you should have taken 7, but you may have a small change, small reduction in your MU.
So is there like okay to like if there's some like point like less than point?
If you think what I'll say is, if you make the mistake of not looking at that one and then you realize that you made the mistake, just look at how much difference is there between the effective span and look at how much difference is there between the right one and the one which you took. Okay, if it's not such a big difference, just make a note and leave it. No need to rework the whole thing again. Okay.
Okay.
The problem will come if this, for example, this is actually I should have taken 7. If this effective span was coming say 7.5 or more than 7.5, then maybe it's a little bit of a problem. I should have probably rechecked MU and check my design. But
so till 0.5 we can like manage with this, like what is suppose if we calculate it.
Depends. See, for example, if it is for example, if it's a 2 meter beam, difference between 2 and 2.5 itself will be 2.15 itself may be a bit problematic, but between 7 and 7.15 it's not such a big difference. Okay, you have to look at both the numbers as a whole. Don't just look at the decimal point difference. Okay. See, you just think the difference between 1 and 1.5. It's a much bigger difference than looking at a difference between 7 and 7.15. Correct now?
Yes, sir.
Just like that you decide, okay?
Yes, sir.
But anyway, best thing is to not forget to make that check, like what I did over here. Okay, fine, I think I'll close. I think you're also out of time, I'm also out of time. Okay, bye. We will meet on Wednesday again.
So Wednesday is holiday, sir.
Then Thursday. What is on Wednesday?
Online
Sir,
break.
from
Sir.
Wednesday to Sunday, it's
That's
break
online.
week, sir.
Okay, fine. Why am I not able to exit the meeting? Okay, people leave. You people can leave. It's taking a bit of time for me to exit it. You people can leave the meeting. Meeting.